And a significant number of Filipinos are now dealing with the chronic disease diabetes.
Diabetes remains a major public health concern in the Philippines.
Diabetes, you don't know you have it until you actually get tested for it. Because
according to the World Health Organization, an estimated 830 million people worldwide were living with diabetes.
Why should we be aware of diabetes? In fact, an estimated 3 to 4 million Filipinos have diabetes.
In the Philippines, diabetes is expected to affect some 4.7 million Filipinos.
On diabetes say they're increasingly concerned about the mental health impact that managing the disease has on patients, especially young women.
I would go to sleep at night and think, this might be my last night. I might not wake up and see my daughter ever again.
What if diabetes can be challenged not with medicine alone, but at the level of our genes?
What if the secrets of type 2 diabetes were hidden in our DNA?
What if we could target the exact genetic variants that causes this disease?
What if we could design the perfect guide, an sgRNA, to strike with precision?
What if those genes were not only powerful, but safe?
What if computers become our laboratory, testing these designs in silico?
And what if this journey brought us to a future where treatment is not one size fits all, but written in your very own genes?
And this is our journey.
In silico design of sgRNAs for CRISPR-Cas9, targeting significant variants in key genes associated with type 2 diabetes.
Diabetes isn't just a word. It's a silent challenge faced by millions worldwide. Every second, lives are changed by this condition that affects how our body uses sugar for energy. But what if science could strike at the root of our very genes? Through the power of CRISPR-Cas9, we explore how targeting key genetic variants may unlock new possibilities in understanding and managing type 2 diabetes.
Type 2 diabetes is a global health challenge mainly caused by key genetic variants related to type 2 diabetes that shape how our bodies creates, reacts, and respond to insulin. Understanding these key genetic variants is helpful in order for us to develop treatment and prevention strategies.
Our study aligns with SDG 3, good health and well-being. By targeting genetic variants linked to type 2 diabetes, we're looking at new ways to understand, prevent, and someday improve treatments for millions worldwide.
Also supports SDG number 9, Industry, Innovation, and Infrastructure. We use innovative in silico tools and CRISPR-Cas9 design, showing how science and technology can push the boundaries of modern medicine.
And for SDG 12, responsible consumption and production. Our computational approach is cost-efficient and eco-friendly. We reduce the need for excess lab resources, making research both sustainable and impactful.
Through these goals, it proves that science isn't just about discovery, it's about responsibility, innovation, and improving lives.
Our sequence involves obtainment, designing, on-target and off-target scoring of the sgRNA, and off-target analysis.
The researcher used BenchLink to design sgRNAs for genetic variants linked to type 2 diabetes, including different genetic variants using the Homo sapiens GRCH38 model. After uploading the sequences and selecting CRISPR, BenchLink generated sgRNAs with efficiency and specificity scores. Based on Dowench et al. 2016, sgRNAs with on-target scores above 60 and off-target scores above 50 were chosen to ensure stability, accuracy, and potential suitability for CRISPR-Cas9 gene therapy in type 2 diabetes.
To assess sgRNA off-targets, the sequences are exported to CASaFinder, where a mismatch threshold is set. The tool scans the genome for similar sequences and generates a report detailing off-target sites, mismatch counts, and chromosomal locations. Guides with fewer off-targets are prioritized for validation and experimental use.
Our study is mainly focused on targeting 5 genetic variants related to type 2 diabetes. We use BenchLink to guide RNA designing and CASaFinder for off-target scoring.
The results showed that KCNJ11 showed the highest efficiency with an ON score of 73.9, while TCF7L2 and IRS1 both stood out for their high specificity with an OFF score of 79.6.
On the other hand, SLC3088 showed the most suboptimal performance in specificity at 52.1 and 24.7, while the other genetic sequence showed a lot of problems. This includes moderate performance and low specificity.
When we analyze off-target effects, we saw that mismatch tolerance and bulge types, especially RNA bulges, greatly increased the number of off-targets. For example, some guides produce hundreds of unintended matches at 3 mismatches.
A 1-way ANOVA also confirmed there were no significant differences across the sgRNAs overall, meaning variability came more from sequence composition and mismatch tolerance than from one gene variant being consistently better.
Science is more than just a theory, it's hope. And with CRISPR-Cas9, we're not just studying about DNA, we're rewriting possibilities for future health.
Our results give a glimpse of what's possible. Today, they are computer models. Tomorrow, they could guide real experiments. And for the future, they might actually help for the problem we're currently facing.
This process reminds us that in research, every detail matters. One sequence, one score, one choice. Each will define our way we fight diabetes for the years to come.